Thanks everyone for holding in there. So just going to take you on my Wayback Machine and realized I have 2 degrees of relatedness to Kevin. One is my foray and rotation to the Clinic for Special Children, and the other is I graduate of UMass Chan. So about 30 years ago, I traveled the back roads from Baltimore to Lancaster in the dark. 2 hours each way for about a month to do a rotation at the Clinic for Special Children. And at the time, I was a pediatric resident, and I was really interested in neurology, but I had seen some patients during my pediatric residency at Johns Hopkins, specifically a urea cycle disorders patient, and really was interested in these disorders because, as you know, many of these affect the brain. And so I thought, is there a role for me in establishing a research program where I could be a neurologist, also a geneticist, and sort of understand that interface of, what's happening in the brain at a time when we didn't really have a lot of technology or even interest in looking at that. And I think for many years, the bar was very low. These are the disorders, this is what happens, and, that's all we can do. So I met my first MSUD patients. I worked with Holmes Morton. He showed me his GC-MS machine in the back of a clinic that really looked quite simple from the outside. I pulled up my car between hitching posts and met Rebecca, who is a Mennonite woman who was the office manager. Holmes and his wife learned that he played the fiddle. And from there, just saw families and patients and was immersed in yet another metabolic disorder and decided, yeah, this is what I want to do. So back and forth, 2 hours each way, and really brought back a lot of experience, a lot of knowledge about what it's like to walk in the shoes of patients and families with these disorders. So we're going to switch to the brain now and talk about some of the work that my group's been able to do with the generosity of a grant from the MSUD Family Foundation. And I also wanted to acknowledge my colleagues, Kosar Kaksarki, who's the biomedical engineer, and Anna Moreno-Chaza, who's the research coordinator. And you will have the opportunity, if you'd like, to participate in these studies. So we're going to talk about some preliminary research findings. So I think we all know the problem, and just for the sake of time, I won't do all these slides in excess, but we know that certain amino acids in MSUD are toxic to the brain, and they interfere with energy metabolism, with other functional aspects of the brain. And so the downstream effect that I'm interested in looking at is how do we get from the biochemistry, the amino acids, the decrease in of neurotransmitters, so glutamate, which is an excitatory aminotransmitter, which then makes GABA, which is an inhibitory neurotransmitter and can protect the brain from excessive excitotoxicity. How do we get from there to some of the cognitive issues we see in patients, particularly executive function? Is there a non-invasive way to measure it? And so I'm going to talk about how we are trying to understand the effects of MSUD on the brain, previous neuroimaging research that's been done in this field, which isn't really that much, and then how new tools such as near-infrared spectroscopy can help us understand more function. So the pictures that Dr. Strauss showed you is the structure of the brain, but can we go beyond that and look at function in real time? And so again, this has been covered before, is that what is the connection between altered metabolism from a genetic defect and the downstream functional effects? And so my team is interested in using non-invasive neuroimaging technology, so more like a brain-computer interface, like how are circuits affected because of this biochemical abnormality from the gene not working? And then do we have tools that we can use? And more importantly, what are those tools telling us about functional consequences? And do we have a way to ameliorate that? Like, once we see what the problem is there some strategy to overcome it? Can we use these as endpoints for some of these therapeutic trials? So we all know that MSUD is a spectrum and not everyone is the same. I usually tell my students, once you meet a patient with X disease, you've met one patient with X disease. Everybody has their nuances. That could be due to enzyme activity, other genes in your genome, environmental effects, which can explain some variability. And we know that the classic MSUD has the most consequences, but also intermediate MSUD may have very subtle but real brain effects. And so why is the brain vulnerable in MSUD? Well, the brain has very high energy needs. It consumes almost all of the energy and requires more oxygen than most other organs in the body. And it needs to maintain a very sensitive chemical balance. So it relies on this delicate balance of amino acids and neurotransmitters so that if there's any disruption or imbalance in the ratio, that can quickly impair brain function. And also the brain is, one of the few, if the only organ that's still developing. So although an infant is born with a normally formed brain and you have all the neurons or nerve cells you're going to have, the process of myelination. So myelin is that thick, fatty white substance which coats the neurons and connects. It's basically the connecting cables, so connecting one neuron to another. That's still developing, and that still develops over the first 2 to 3 years. And so any early insults can affect that process. And then we all heard about the metabolic crisis in MSUD with brain swelling. So there are different repertoires to which the brain can respond to a crisis or not respond. So we see swelling, and that can be lethal in some cases. The signaling is slowed down, and there's also a risk for seizures and coma. So, how do we predict metabolic crisis and how do we avert it is really important. Not surprisingly, there's been very little MRI research in MSUD. Most of the data in humans has been in older children or adult studies. There are really no functional studies of how these patients are performing, things like functional MRI. They're all basically structural and diffusion weighted. So that shows us how much water is in the brain. From those studies, we know that there may be early white matter changes, and again, because the white matter, the myelination, is a process that's ongoing, so it can be impacted by any imbalances. You have edema, and then there can be some MRI abnormalities that can improve after treatment and metabolic stabilization, so there may be some partial reversibility, but does that mean that the function improves? And so see some of the previous studies here, not very many. Now, in my other work, my other hat, working in other inborn errors, I spent 20 years working on urea cycle disorders, still working on it, and we used in-scanner, so in the MRI scanner with different sequences. And, we need some gentler tools because not everybody can perform in the scanner. It requires sedation or anesthesia for younger children, so it's hard to justify research studies when you have to use anesthesia. And additionally, that patients with inborn errors of metabolism who would have to be fasted for anesthesia or even getting the anesthesia is another level of risk. MRI predominantly shows structure but not function. MRI is expensive, so in order to do 1 hour on the research scanner, it cost me like $800 per subject just for that 1 hour from my grant. An MRI is loud, so it's very inconvenient for many people. Some people are claustrophobic, and it's definitely not portable. And so partially by interest and partially by the consequences of the COVID pandemic, we've moved a lot of our studies to functional near-infrared spectroscopy. One reason being that because these are rare disorders, which I study, everything shut down during COVID. We're no longer able to bring patients from across the country to the scanner. And rather than just say we're done and we don't want to study what's going on in the brain anymore, we had to pivot to new methods. And so fNIRS is sort of a field that, it's been around, but a lot of people haven't really been using it, and certainly not in rare disease space. So this was a good opportunity to see how it performed and what type of information it could give us relative to the more standardized imaging treatments. And so why do we like fNIRS? Well, here's a child here, and these pictures are all courtesy of NIRX, which is the device that we use, so these aren't our individual patients. It uses near-infrared light. It's non-invasive and portable, so we actually have it here. It can be taken through TSA. It's kid-friendly. It doesn't hurt. It's comfortable. It doesn't make any noise. There's no magnets or magnetic field, and it's more affordable than any other brain imaging method. So once you actually buy the device, you realize the cost savings by the multiple times you can use it. It's not the $800 an hour type of investment, which limits the amount of subjects you can do. So why would fNIRS be suitable for MSUD? So with this device, we're actually detecting brain function. So that's what we want to know, is what is the function of the brain as a result of the biochemical defect. We obtain real-time imaging. The patient's right there in front of us. We can measure them at rest. We can measure them with various tasks. It can be repeated. It can detect early stress in the brain. It's portable. So we can go to the patients wherever they are, and that's really important in populations of rare disease. And the other thing is it's portable in terms of the patient can actually wear it and walk around. So you could pair it with other types of sensors or devices if you wanted to look at movement. They could have wearable sensors or devices plus that. So the possibilities are endless in terms of pairing it with different devices. And we've actually developed a driving simulator to look at executive function, where we have an actual car seat and pedal and steering wheel, and the patient's wearing the fNIRS. So you can have multiple uses for the fNIRS with other studies. And so this was a small study. These subjects were obtained during the last meeting in 2024. And so we had 30 subjects. Most of them were MSUD and 9 controls. And then during the last symposium, 21 participants were recruited, 17 with MSUD and 4 controls. So we thank you for the community participation, and we appreciate that. We did recruit some subjects at Children's National, where I was previously, and we had 2 different types of tasks. For those who are under 8, they watched cartoons during the scanning. One was Timmy Time, which has, they're both videos, very short clips. One has language and one doesn't. So the second one was Peppa Pig. They both focus around a musical instrument story, so they're similar. And so the Peppa Pig has the language, the Timmy Time, the song introducing the cartoon has words, but then the rest of it has to be inferred by the subject watching it. And for older subjects, we did a computer-based task called the NBAC test. And so this is a test that can be done auditory or visual. The visual NBAC is you look at a series of letters, and then you press the space bar. If the letter you're looking at currently is 1 back from the one you saw before, that would be a 1 back test. And then the 2 back is like the letter sandwich. So it might be B, A, B. So you recognize that you saw the B 2 back, and you press the space bar. So this is a test of working memory and also processing speed. And then we had some infants, but we didn't have infant control groups, so we didn't put them in our final analysis. And so this is our younger than 8-year-old patients who watched the 2 videos. And so what we saw was interesting is we saw that actually the activation in the back of the brain was enhanced, and that might be because they were visually engaged in watching the video. So we looked at 6 different regions of the brain. This is oriented so that this is the top of the brain, and this is the bottom. So you're like looking down onto someone's brain. And this is the left side, and this is the right side. This is the prefrontal cortex. So this is where your executive functions are coming from, working memory, attention. And this is very dopamine rich in terms of the neurotransmitter. And then we have the parietal regions here, left and right. These are more like your association cortex and putting things together. And then occipital is more your vision. But all of these have to work together. And so what the fNIRS measures is it measures blood flow, basically. So when you perform a task, oxygen goes to that part of the brain, and the oxygen is extracted. So you have two states. You have oxygenated or oxygen-rich blood, and then you have deoxygenated blood where it's been pulled out, and then you have the total. So we can measure all three of those parameters, and we can show, any differences in terms of the oxygenated component and the deoxygenated component. And that gives a signal difference that can be calculated during this technology. And then for those who are over 8 who did the NBAC visual with the letters, we saw a slightly different pattern. So basically what this technology can show us and these tasks can show us, and the tasks are fit for purpose. So we understand what the cognitive problems may be, and we try to design the task around that so we can bring out those differences. Is that in this case, the deoxygenated hemoglobin part was more significant here on the left occipital region. So there are differences, and what does that mean? And then when we look at audio, again, this part seems to be more impacted. And so what were some of the key findings? So one was a feasibility. Can we do it? And yes, we were able to get good data for the most part. It's a little difficult with movement, but definitely not as bad as movement in the MRI scanner. That we were successfully able to capture brain activation in the patients and controls, that both groups showed the strongest activation in the prefrontal region, that occipital activation during the language tasks could be explained by the visual processing, and that both groups of subjects had similar task performance, and that the group differences may indicate that there are subtle differences in brain function in MSUD. And that's something, we have a very small number, so we need more subjects to be able to see if that withholds, that theory withholds time. So we think that fNIRS is a promising tool for mapping the brain. It can pick up subtle differences. This kid's very happy wearing it, so it's very safe and it's comfortable. And the findings indicate that there is preserved cognitive function, but altered brain physiology in MSUD. So it's looking at different domains of cognitive function. So what does that mean for families, and what might we want to use this in the future? So one thing that I envision is once we understand the full trajectory of activation patterns across the spectrum of MSUD, and we also need more clinical information. So this was done without us knowing which genetic variants you had, age of diagnosis, how many hospitalizations you had, if there was any edema or previous metabolic decompensation that required ICU admission. These were mainly feasibility studies. So coupled with that, we'd like to kind of go in the Wayback Machine and see, could we detect things earlier? Is there some signal, if we follow patients over time, that may indicate that there could be a risk for metabolic decompensation? Can we detect something earlier? Can we monitor patients? And hopefully this can provide a more hopeful future as we understand how this relates to the cognitive phenotype that we see or the manifestations that we see, and might we be able to develop some practice technology that we can help people overcome some of the executive function issues, and possibly driving, looking at driving in this group as well. As a real world stressor, we know that some patients may only have cognitive issues under periods of stress or illness. So can we use something like a driving simulator to mimic a stressor in real life? And so I'd like to thank our family support group who provided us with a lot of encouragement for this study and also funding, and then of course our participants. So thank you very much.